One of Jupiter's mysterious moons, Europa, hides a secret beneath its frozen crust. There's an immense global ocean, potentially teeming with life, sealed and hidden away in darkness for millennia. Recently, NASA launched its Europaclipper mission, which is yet to unravel the mysteries of this alien world. Beneath the frozen surface, hydrothermal vents may create ideal conditions for life forms to thrive, just as they do in the deepest parts of Earth's oceans. But how do we explore these extraterrestrial worlds, and what secrets might they reveal? Europaclipper is one of NASA's most ambitious endeavors, aimed at studying the habitability of icy moons. It was launched in October 2024. It was built to study Europa, one of Jupiter's moons long suspected to harbor a huge subsurface ocean beneath its thick, icy shell. The Clipper mission is set to reach Europa in the 2030s, and its primary goal is to assess whether this moon can support life as we know it. Equipped with top-of-the-line tools, the spacecraft will embark on a multi-year journey through the solar system. Once it reaches Jupiter's orbit, Europaclipper will make dozens of close flybys of Europa, gathering unprecedented data about its structure, composition, and most importantly, the possibility of life on this moon. The mission's particularly significant because for the first time, a spacecraft will focus on the viability of an oceanic world, expanding our understanding of where life might potentially exist in the universe. Though Europa's surface may seem frozen and uninhabitable, it could be one of the most promising life-sustaining environments beyond Earth. Beneath its icy exterior lies a global ocean, potentially holding more than twice the volume of Earth's oceans. It's theorized that the thick ice layer shields the ocean from harsh radiation, while tidal forces from Europa's proximity to Jupiter cause significant flexing and heating, possibly keeping the water in a liquid state. On board Europaclipper is an impressive suite of scientific instruments, each designed for specific tasks. The ice-penetrating radar will help scientists measure the thickness of the ice and determine if there's any interaction between the ocean and the surface. The spacecraft's spectrometers will be used to analyze the chemical composition of the surface, examining it for compounds that might hint at biological processes. Meanwhile, magnetometers will map Europa's magnetic field, providing clues about the ocean's depth and salinity. Thanks to these repeated flybys, Europaclipper will be able to provide researchers with detailed insights into the icy shell, the ocean, and the potential hydrothermal activity of this moon. The data gathered by the mission will be crucial in determining whether Europa's ocean contains the chemical energy necessary to sustain life. However, Jupiter's radiation poses a significant challenge for any spacecraft in its vicinity. The planet's magnetic field is 20,000 times stronger than Earth's. It traps charged particles that race around the system at incredible speeds, creating an intense radiation zone bombarding nearby moons with ionizing radiation, including Europa. For Europaclipper, the challenge lies not only in surviving this high-energy environment, but also in protecting the delicate onboard electronics from being damaged by the radiation. The electronic systems of the craft, including the central computing units, scientific tools, and communication systems, are shielded from radiation. The protective casing, made from a combination of aluminum and zinc, is a vital defense against radiation exposure. But even with this protection, Jupiter's radiation is so intense that some components, particularly the transistors used in Europaclipper's instruments, may still prove to be vulnerable. Transistors known as MOSFETs, metal oxide semiconductor field effect transistors, are essential for controlling the flow of electricity throughout the spacecraft. These components are especially sensitive to ionizing radiation, which can alter their electrical properties and lead to failure. Recent tests have shown that these transistors fail at lower radiation doses than initially predicted, and that raises concerns about their reliability once Europa Clipper reaches Jupiter's orbit. To mitigate the risk, NASA engineers to assess how many transistors could go out of commission during the mission and how severe the consequences might be. They're exploring ways to extend the life of these components through software and operational workarounds, such as limiting exposure to the highest radiation zones and using redundancy in systems where possible. Despite the precautions, there's no simple solution. The spacecraft's electronics vault was sealed in 2023, making any hardware changes impossible without significant delay. Over the last few months, the mission team has been weighing the risk of semiconductor vulnerability against the high cost and potential delay associated with unsealing the vault and replacing parts. If the electronics stop working prematurely, it could jeopardize the operation of critical systems. However, the mission's design includes built-in redundancies and operational flexibility, allowing the team to work around certain failures by relying on backup systems. NASA's task is to ensure these failures do not impede the mission's primary scientific objectives, especially the exploration of Europa's icy surface and the ocean beneath it. Now, let's take a closer look at these oceans. So, as we've already mentioned, there are vast oceans hidden beneath the icy shells of Europa and Enceladus, potentially some of the most promising places for finding life beyond Earth. It's believed that these concealed oceans, kept in a liquid state by the tidal forces of their parent planets, contain key ingredients necessary for life: liquid water, energy sources, and essential chemical elements such as oxygen. But how exactly could we measure the potential for life in these alien oceans? The answer lies in how oxygen and other chemical elements are produced and distributed beneath the icy layers. On Europa, one of the most important factors for assessing habitability is oxygen. Although Europa is constantly bombarded by high-energy particles from Jupiter's magnetic field, this radiation is more than just a threat to technology. It could also contribute to oxygen production. When these charged particles collide with Europa's icy surface, they break water molecules into hydrogen and oxygen. While most of the hydrogen escapes into space, some of the oxygen remains in the Moon's atmosphere or enters the subsurface ocean through the cracks and brine channels in the ice. The current theory is that this water-splitting process is one of the main ways oxygen enters Europa's ocean. However, recent studies have shown that previous estimates of oxygen production on Europa may have been overstated. New data, particularly the measurements taken by NASA's Juno probe, indicate that the amount of molecular oxygen present around Europa is much lower than previously believed. This data suggests a more limited oxygen entry into the subsurface ocean, potentially narrowing the range of conditions in which life could exist. According to the latest data, Europa produces around 26 pounds of molecular oxygen per second. That's a far cry from the earlier estimate of up to 2,000 pounds per second. This revised figure has led scientists to reconsider the question of how much oxygen actually reaches the ocean and whether this amount is sufficient to support oxygen-dependent life forms. Despite the lower than expected oxygen production numbers, Europa remains a prime candidate for harboring life. Even at these low levels, this Jupiter moon produces enough oxygen to sustain life in a unique, potentially energy-efficient form. The process is occurring on Europa, where oxygen may seep into the ocean through cracks in the ice, may resemble Earth's deep-sea environments, where life exists without sunlight, relying on chemical energy. In particular, this energy could be provided by hydrothermal vents on the ocean floor. Hidden beneath thick ice in eternal darkness, these vents may offer chemical and thermal energy supplied by hydrothermal activity, just as hydrothermal vents discovered in Earth's deep oceans. These vents, acting as natural chimneys, release mineral-rich heated water from the rocky depths of the moon, creating a potential haven for the emergence and flourishing of life. On Earth, hydrothermal vents are home to unique ecosystems that don't rely on sunlight. Instead of depending on photosynthesis, the life forms around them derive energy from a chemical reaction between water and minerals, a process known as chemosynthesis. Astrobiologists believe that if life exists on this moon, it could thrive in a similar way. Unlike Earth's deep-sea black smokers, which are powered by the planet's molten core and can reach temperatures over 700 degrees Fahrenheit, hydrothermal vents on these icy moons are expected to be much cooler. The absence of a molten core on Europa and Enceladus raise questions about the sustainable existence of high-temperature vent systems. However, new models suggest that low-temperature hydrothermal vents may have persisted on these moons for billions of years, providing long-term stability and a source of heat. These low-temperature vents should operate similarly to those found on Earth's seabed, for example, along the Juan de Fuca Ridge in the Pacific Ocean. On Earth, cold seawater is drawn into the seabed, where it circulates through ancient volcanic rocks, gradually heating up before re-emerging through other vent openings. This process not only heats the water, but also alters the chemical composition, producing the necessary ingredients for chemosynthetic life. Organisms like tube worms and extremophiles thrive by utilizing hydrogen sulfide and methane released from the seabed. Europa is intriguing not only because of its hidden ocean, but also due to its dynamic surface activity. Recent observations, particularly from NASA's Juno mission, have provided new insights into the water plumes, jets of vapor escaping from beneath the moon's icy crust. These plumes, first spotted by the Hubble Space Telescope and now confirmed by multiple missions, give scientists a tantalizing glimpse of what lies beneath Europa's frozen shell. When the Juno spacecraft went past Europa in 2022, it captured high-resolution images of the Earth's surface, revealing complex features such as ridges, chaotic terrain, and scars that may indicate regions of recent activity. Also, the most significant findings were areas believed to be the source of water vapor plumes. These towering jets shooting as high as 120 miles into space are thought to arise from cracks in the icy crust where salty liquid from the subsurface ocean meets the near vacuum of space and quickly evaporates. Studying these eruptions is crucial for several reasons. Firstly, the substance expelled from Europa's interior can be directly analyzed by the instruments on the passing spacecraft. This gives scientists a unique opportunity to examine the chemical composition of the subsurface ocean without the need to drill through a thick layer of ice. These plumes may contain a mix of water, salts, and possibly even organic molecules. By measuring the chemical composition of the vapor and particles in these plumes, scientists hope to gain deeper insight into the ocean's potential to sustain life. Detecting key elements such as oxygen, methane, or even amino acids would be a significant indicator that Europa's ocean contains the necessary ingredients for life. The composition of these plumes may also reveal the salinity of the water and the interaction between the ocean and the rocky seabed. Both are crucial factors for determining habitability. In addition to plumes, certain regions on Europa's surface, such as the platypus, suggest that liquid water might be closer to the surface than previously assumed. The chaotic terrain of the platypus is a disordered cluster of ice blocks and ridges, likely formed by the seeping of salty water from below the surface and the alteration of the ice surface. This feature, measuring 23 by 42 miles, is considered geologically young, hinting at ongoing activity beneath Europa's frozen crust. Surface activity on this moon continues to provide important clues about what might be happening under the ice. These eruptions not only offer insight into the composition of the subsurface ocean, but also provide valuable information about the processes driving this activity, processes that may resemble conditions on early Earth. Meanwhile, Europa's surface is dynamic and constantly changing under the influence of Jupiter's powerful gravitational forces. The Moon's icy crust is composed of large, rigid plates that float above the subsurface ocean, moving and interacting not unlike the tectonic plates on Earth. These movements create fractures, ridges, and chaotic terrain, altering the surface and possibly affecting what lies beneath. Other research of these same recent images of the platypus feature captured by Juno has revealed intriguing details about the behavior of Europa's ice plates. In this case, the point of interest is a complex arrangement of ice blocks, which suggest ongoing surface processes. These blocks, some reaching up to 1 kilometer across, are separated by cracks, indicating that the plates may shift or rotate. It's theorized that this activity is caused by the constant tidal flexing that Europa experiences as it orbits Jupiter. As these icy plates move and break apart, they may create pathways for the subsurface ocean water to reach the surface. In some regions, this process could lead to water seeping through the cracks, depositing dark, low albedo material, which may serve as potential evidence of salty liquid emerging from below. By comparing the latest images from Juno with the older data from the Galileo mission, researchers have noted potential changes on Europa's surface. The southern region of the platypus appears wider in the Juno image, and the morphology of the block beneath the eyes looks different in the two data sets, suggesting surface evolution. Although these signs of changes that took place since the Galileo mission are not definitive due to differences in image quality, they may suggest ongoing geological activity. The interaction between the plates may have led to localized melting of ice, or even the emergence of new surface features as salty water from the ocean rises and freezes. Understanding these surface processes is critical, as they directly impact the possibility of accessing samples of subsurface material without drilling through Europa's thick ice shell. If these ice plates regularly move and crack, it could provide a natural pathway to the ocean beneath. Europa and Enceladus. Both of these icy moons are amongst the most promising candidates in the search for extraterrestrial life within our solar system. Now let's summarize. What exactly are the signs of life we should expect to find? And how do Europa and Enceladus compare in their potential to support life? One of the most significant potential signs of life on these moons is the water vapor plumes erupting from their surfaces. On Enceladus, spectacular geysers shoot water, salts, and organic compounds hundreds of miles into space from its south pole. These plumes serve as direct evidence of a subsurface ocean in contact with the moon's rocky core, a crucial factor for sustaining life. On Europa, indirect signs of similar plumes have also been observed. Both moons are also suspected to have hydrothermal activity in the depths of their oceans, where heat and chemical energy are generated as a result of interactions between ocean water and the rocky core. On Earth, these kinds of environments teem with life, suggesting that similar processes on these icy moons could support microbial ecosystems. While the plumes on Enceladus provide easier access to samples from the chemical makeup of the ocean's depths, Europa's thicker ice shell might conceal more complex, long-term interactions between the surface and the ocean, making it equally intriguing for future research. The Europaclipper mission, launched in October of this year, is a critical step in this search. Although the spacecraft will not land on Europa itself, it'll conduct approximately 50 close flybys, collecting data to determine whether Europa's environment can support life. Europaclipper's instruments will analyze the moon's icy surface, measure the thickness of its ice shell, and study the composition of the subsurface ocean via its plumes and the chemical makeup of the surface. Signs of life on Europa and Enceladus are likely to be subtle, but if amino acids or other organic compounds are discovered, it may serve as compelling evidence that these moons are habitable. Recent studies suggest that biosignatures on Enceladus may be preserved at much shallower depths, making it easier for future missions to detect them without extensive drilling. On Europa, where the ice shell is thicker, scientists have estimated that amino acids may be preserved beneath the surface at greater depths than previously thought, especially in areas shielded from radiation. Discoveries made by Europaclipper could pave the way for future missions, including potential landers built to dig deeper into the ice and access the aforementioned preserved biosignatures. Landers could directly sample the ice, study the subsurface layer for chemical signs of life, and even explore active plume regions to capture materials from the ocean beneath. Europaclipper has already embarked on its journey, and the stakes are high. This mission will not only provide a clearer understanding of this distant world, but also serve as a model for future missions to explore the icy moons of our solar system. Whatever Clipper discovers may very well change our perception of life in our universe and certainly open new horizons for exploration, revealing whether life has found a way to thrive in the hidden oceans of distant worlds. Imagine a world where the oceans are covered in ice, where glaciers extend as far as the eye can see, and where even the equator, a region synonymous with warmth and sunshine, is a barren, frozen wasteland. This is not the setting of a science fiction novel. This is Earth, but not as you know it. Welcome to the mystery of an ice-covered planet that scientists are still trying to solve. You might think that a few cold winters are unbearable. But what if a winter lasted 100 million years? It's a question that not only boggles the mind, but also calls into question our understanding of Earth's climate system. How could a planet teeming with life suddenly turn into a frozen ball? And more importantly, how did it escape from this icy prison? These questions have puzzled scientists for decades, and the answers are as complex as they are fascinating. So, buckle up as we embark on a blood-chilling expedition to understand why the Earth has been frozen for an unimaginable 100 million years. Our planet has been traveling through space for about 4.5 billion years, and during this long journey, its climate has not been static. From the scorching heat of Hayden Eon to the lush green landscapes of the Mesozoic era, Earth wore many climate suits. Each epoch tells a unique story, a chapter in the history of Earth's ever-changing climate. The Cambrian period, for example, was a time of warm tropical seas, whereas in the Permian period we see a world struggling with extensive glaciation. You may be wondering, are these climate shifts just part of the natural cycle? To some extent, yes. The Earth has oscillated between ice ages and warm periods known as interglacials. These cycles are influenced by many factors, from solar radiation to ocean currents. But here's what gets intriguing. These natural cycles don't fully explain the extreme case of the 100 million year freeze. This is an anomaly, a deviation from the norm which requires deeper investigation. Imagine the equator, normally a belt of warmth and biodiversity, turned into a frozen swath of desolation. This was not just another ice age. It was a freeze of epic proportions, a climate event so severe that it challenges our understanding of Earth's natural systems. When it comes to unraveling Earth's icy mystery, rocks are like the pages of a history book. each layer telling the story of past climates. One compelling clue lies in the form of drop stones, stones that had been carried by glaciers and dumped into what once had been ancient seas. These falling rocks can be found in places you'd least expect, such as the center of today's vast deserts. Their presence is a geological whisper, hinting at a time when ice covered even the most unexpected places. Ice cores are another invaluable piece of the puzzle. These cores, extracted from the bowels of polar ice sheets, contain tiny air bubbles, each one a snapshot of the atmosphere at different points in time. By analyzing these ancient air pockets, scientists can reconstruct past levels of carbon dioxide, methane, and other gases. The data paints a frightening picture, a sharp drop in greenhouse gases during the Great Cold Snaps. Fossils open another window into this frozen past. Remarkably, even in harshest conditions, life found a way to survive. Microbial fossils tell us that simple life forms continued to exist and even thrive during this long freeze. These resilient organisms may have clung to life near underwater thermal springs or other warm microenvironments. Their survival is a testament to the resilience of life, even as the Earth itself plunged into an endless winter. Falling rocks, ice cores, fossils, each piece of evidence adds a new level of understanding to the complex tapestry of Earth's climate history. So what could have caused such a long freeze, and how did Earth, a planet teeming with life, survive the icy ordeal? One of the leading theories that could explain this prolonged freezing is related to Earth's orbital patterns, known as Milankovitch cycles. These cycles describe how the Earth's position and orientation in space change over time, affecting how much sunlight reaches the planet. While these orbital shifts are associated with shorter ice ages, they cannot explain a freeze-up that lasted 100 million years. The cycles are simply not long enough to explain such a long period of cold. Another theory points to volcanic activity as a potential catalyst for cooling. Strong eruptions can release ash and gases into the atmosphere, blocking sunlight and causing temperatures to drop. However, the cooling effect of volcanic eruptions is usually short-lived, ranging from a few years to a decade. It's unlikely that volcanoes alone could plunge the Earth into a winter of 100 million years. The carbon cycle is another contender on the list of theories. This complex system regulates the level of carbon dioxide in the atmosphere, a key factor in Earth's climate. Disruption of this cycle could theoretically cause carbon dioxide levels to plummet, setting the stage for deep freezing. But again, the question arises, could such a collapse have lasted 100 million years? While each of these theories describes a piece of the puzzle, none can fully explain the mystery of freezing for 100 million years. It's likely that a combination of factors, some still unknown, contributed to this extraordinary event. So if Milankovitch cycles, volcanic activity, and the carbon cycle can't fully explain this icy mystery, what can? Among the theories attempting to explain the prolonged freezing of the Earth, one stands out for its boldness: the snowball Earth hypothesis. This theory asserts that the Earth is not just partially covered with ice, but is completely encased in it from pole to pole. In this frightening scenario, even the oceans would be frozen, at least on the surface. Imagine a world where the seas are solid and the skies devoid of clouds because even the moisture in the atmosphere would freeze. The path to becoming a snowball Earth will involve feedback loop. That's a circular effect that's amplified. As the ice expands across the surface, it reflects more sunlight into space, further cooling the planet and leading to even more ice formation. This feedback loop could be caused by any number of factors: a decrease in greenhouse gases, a decrease in solar radiation, or even the configuration of continents affecting ocean currents. The snowball Earth hypothesis is not without critics. Some scientists argue that complete freezing would make the survival of life impossible, which contradicts the fossil record, which shows that life persisted throughout this period. Proponents counter this by suggesting that life may have survived in pockets of liquid water near submarine thermal vents or within the Earth's crust. The debate continues, and new data are constantly changing our understanding of this icy mystery. The snowball Earth hypothesis puts our understanding of climate extremes and the sustainability of life to the test. Whether you find it compelling or controversial, it offers a fascinating prism through which to explore the mysteries of Earth's climactic past. In a world covered in ice, one would expect life to stop. However, the fossil record tells a different story. Microorganisms appear to have survived this extreme climactic event. These microscopic life forms may have taken refuge in the deep sea near hydrothermal vents or even in the Earth's crust. Extreme conditions often act as a crucible of evolution, and the Great Freeze was no exception. The urge to adapt or perish may have led the emergence of new life forms, some of which may be the ancestors of the species that inhabit Earth today. Fossils from this period show an amazing diversity of life, suggesting that freezing temperatures may have catalyzed evolutionary innovation. How did life exist in a frozen world? One theory suggests hydrothermal vents on the ocean floor served as warm refuges. These underwater oases may offer a stable environment rich in nutrients, allowing life to persist. Other possibilities that would include subglacial lakes or even warm spots in the Earth's crust. This microenvironment may be the last refuge of life, a haven of hope in a world gripped by cold. Microbial resilience, evolutionary pressures, and the potential refuges that allowed life to survive all contribute to an impressive story of survival against all odds during Earth's 100 million year freeze. After 100 million years in ice, the Earth has finally begun to thaw, but how did the planet transform from a frozen sphere back into a world full of life? The mechanisms behind this great thaw are as intriguing as the freezing itself. One theory states that a buildup of greenhouse gases, possibly from volcanic activity, may have started the warming process. As these gases accumulate, they will trap heat, gradually raising the planet's temperature. Ocean currents may have played a crucial role in redistributing heat. When the ice began to melt, the currents began to carry warmer water from the equator to the poles, accelerating the melting. The reactivation of ocean currents will not only spread heat, but will also restore the dynamic climate system, further destabilizing the ice regime. Another factor that may have contributed to the thaw is an increase in solar radiation. Our sun is not a constant star, its output varies over time. A period of increased solar activity can provide the extra energy needed to tip the scales toward warming. Even a small increase in solar energy that raises the Earth's average temperature by just a few degrees could irrevocably alter the climate. This subtle shift can act in synergy with Milankovitch cycles, natural changes in the Earth's orbit, amplifying their effects and contributing to the destabilization of the frozen state. After the ice melts, the Earth's albedo, in other words, the Earth's reflectivity, will decrease, allowing the planet to absorb more heat and further accelerating the thaw. The Great Thaw was probably the result of multiple factors working together, including greenhouse gas emissions, reactivation of ocean currents, and perhaps the impact of our ever-changing sun. And together, these elements rewrote Earth's history, turning the page from a frozen past to a future full of possibilities. The story of Earth's 100 million year freeze and subsequent thaw is not just a journey into the past. It holds lessons for the present and the future. Today, as we grapple with climate change, understanding these extreme historical events can provide valuable insight. Today's climate changes, largely caused by human activity, make the study of Earth's climate history more relevant than ever. Mechanisms that once led to a natural thaw may now be artificially accelerated by anthropogenic emissions of greenhouse gases. Melting glaciers, rising sea levels, and increasing wildfires are stark reminders that our planet's climate is changing. While we're not headed for a snowball Earth, these modern extremes serve as warning signs. The speed at which these changes are occurring is unprecedented in human history, and they reflect the rapid shifts that ended the Great Freeze. Advances in technology offer us tools to study Earth's climate like never before. Satellites and space probes give us a cosmic perspective, allowing us to track changes in real time. However, the same technological advances that enable understanding also drive consumption and pollution, exacerbating the climate challenges we face today. The story of the Earth's 100 million year freeze serves as both a cautionary tale and a source of inspiration. By studying the mechanisms that led to the Great Thaw, we can better understand the levers that control our current climate system. This knowledge is not just academic, it is a vital tool for shaping a sustainable future. In thinking about Earth's climactic past, it's worthwhile to take a step back and consider our planet in a broader cosmic context. The Earth is just a tiny dot in the vastness of the universe, and yet its climate shifts represent a unique example in planetary science. Understanding Earth's climate extremes not only gives us information about our planet, but also gives us insight into the climactic conditions that may exist on other celestial bodies. The study of exoplanets, planets that orbit stars outside our solar system, has increased dramatically in recent years. The climates of some of these distant worlds are even harsher than anything we've seen in Earth's history. By studying these exotic climates, we can improve our models and theories, gaining a more detailed understanding of what makes a planet habitable or uninhabitable. Well, we've already had a video released with an example of a detailed look at such models. The primary goal of planetology is to find an Earth-like planet, the so-called Earth 2.0. Such a discovery would not only revolutionize our understanding of planet formation and climate, but would also have a profound implication for the search for extraterrestrial life. The climate of this hypothetical twin would be of great interest. Could it too experience extreme climate events similar to snowball Earth? And if so, what can this tell us about the sustainability of life in the universe? The story of Earth's 100 million year freeze-up is a complex mystery that scientists are still working on. From initial theories about the structure of Earth's orbit to the bold snowball Earth hypothesis, each idea adds a level of complexity to our understanding of this extreme climate phenomenon. While no single theory can fully explain this prolonged freeze-up, the interplay of multiple factors, orbital changes, volcanic activity, and perhaps even cosmic influences, offers a multi-dimensional view of Earth's climactic past. The wonder and mystery of the Earth's climate are not confined to the past. They are inextricably linked to our present and future. The sustainability of life, the mechanisms of the thaw, and the lessons of today's climate challenges all converge to form a story that is as fascinating as it is instructive.
Imagine a civilization so advanced that it can build colossal structures around stars, capturing their energy and using it for unimaginable purposes. This is not the realm of science fiction. It's a concept proposed by one of the most brilliant minds of the 20th century. A visionary physicist, Freeman Dyson envisioned a megastructure capable of enveloping a star, capturing its vast amounts of energy. This idea, while radical, is rooted in the basic principles of energy consumption and technological progress. But why would an advanced civilization need such a structure? As our civilization advances, our energy needs grow exponentially. But our most ambitious projects pale in comparison to the energy output of our Sun, which releases more energy in 1 second than humanity has consumed in its entire history. Imagine harvesting every bit of a star's energy, turning it into a power plant with nearly limitless potential. If realized, this colossal undertaking would revolutionize how we think about energy and its possibilities. But what would such a structure look like? And even more intriguingly, how would we be able to detect it from our distant vantage point here on Earth? The problem lies in our ability to detect signs of such advanced engineering. While we're just beginning to tap into our planet's energy resources, discovering such an advanced civilization is exciting and frightening. Recent research has revealed unusual infrared signals from 7 distant stars, sparking debate and fueling imagination. Could these signals be technosignatures? Either way, these anomalies defy natural explanations. What's behind these mysterious infrared glows? Are they evidence of advanced extraterrestrial engineering or natural phenomena that we have yet to understand? To understand the concept of Dyson spheres, we must first familiarize ourselves with the Kardashev scale, a method of measuring a civilization's level of technological development based on its energy consumption. In 1964, Soviet astrophysicist Nikolai Kardashev proposed this scale, dividing civilizations into 3 types depending on their energy consumption. Type 1 civilizations use all the energy available on their home planet, including geothermal, solar, wind, and other natural energy sources. Imagine controlling the power of earthquakes and volcanoes to power our cities. This is the hallmark of a Type 1 civilization. Civilizations of the second type go even further, receiving energy directly from their star. This is where the Dyson spheres come into play. By surrounding their star with massive structures, these civilizations can use almost all of its energy. Type 3 civilizations, in turn, are even more advanced and can harvest and harness the energy of their entire galaxy. They control the energy of billions of stars, making them unimaginably powerful. The relevance of the Kardashev scale to Dyson spheres lies in the connection between energy consumption and technological progress. As civilizations evolve, their energy needs grow exponentially, forcing them to develop even more ambitious methods of meeting those needs. But how can we discover the Dyson sphere? One of the most significant milestones in cosmic observation, the development of infrared astronomy, can help us in this challenging endeavor. Infrared astronomy allows us to see the universe in a new light, literally. By observing the infrared spectrum, scientists can detect heat emitted by celestial objects and reveal details invisible to traditional telescopes. This capability has played a crucial role in the search for technosignatures, signs of advanced civilizations beyond Earth. This journey began in the mid-20th century when astronomers used infrared sensors to study space. These early works laid the groundwork for today's sophisticated infrared observatories, such as the Wide Field Infrared Survey Explorer WISE and the James Webb Space Telescope. These instruments have opened a new frontier in astronomy, allowing us to detect faint thermal signals from distant stars and galaxies. But what does this have to do with the search for Dyson spheres? In the 60s, theoretical physicist Freeman Dyson proposed an audacious idea: an advanced civilization could build a massive structure around its star to capture its energy. He envisioned a swarm of solar collectors or habitats orbiting the star and forming what we now call a Dyson sphere. But how could it possibly be detected if it blocked the light of its star? Of course, such a structure would emit vast amounts of infrared radiation, making it visible even from Earth. Dyson's hypothesis was more than just a thought experiment. It provided a viable way to search for intelligent extraterrestrial life. By surveying the excess infrared radiation around stars, we could find evidence for the existence of these colossal structures. This concept led scientists to the recent discovery of several stars with unusual infrared emission. Modern infrared astronomy opens new horizons in the search for Dyson spheres and other technosignatures. By observing the universe in the infrared wavelength range, we can detect thermal emission from celestial objects, allowing us to understand phenomena invisible to traditional optical telescopes. One of the most important instruments in this work is the Wide Field Infrared Survey Explorer. Launched in 2009, WISE has revolutionized our understanding of the infrared universe. Its mission is to map the entire sky in infrared light, revealing countless celestial objects, including stars, galaxies, and asteroids. WISE's ability to detect excess infrared emission around stars plays an essential role in the search for Dyson spheres. By analyzing the heat signatures recorded by WISE, scientists can identify stars with unusual infrared emission, which may indicate the presence of advanced megastructures. One prominent example is the Hephaestus project, led by a team from Uppsala University. This ambitious initiative aims to identify potential candidate Dyson spheres by analyzing Gaia, 2MASS, and WISE data. Hephaestus uses a sophisticated system to sift through millions of stars in search of those with excess infrared emission that natural phenomena cannot easily explain. The project uses machine learning algorithms, including convolutional neural networks, to weed out false positives and identify the most promising candidates. The project's methodology is rigorous. It begins by collecting data from several sources, including precise measurements of the position and distance of stars using Gaia, near-infrared 2MASS observations, and mid-infrared WISE data. This comprehensive data set allows the team to create a detailed model of potential Dyson spheres. The team then uses a grid search method to compare the observed data with theoretical models. This involves calculating the expected infrared emission for different configurations and temperatures of Dyson spheres, and then comparing these models to the observed infrared excess. Through this careful process, Hephaestus has identified 7 potential candidates for a Dyson sphere. All of these objects are M-dwarfs, stars known for their relatively low luminosity, making the detection of infrared excess even more intriguing. These findings are significant because they demonstrate the potential for using long-standing astronomical data for such detections. The quest to detect Dyson spheres and other technosigns is driven by ongoing advances in infrared astronomy. These innovations allow us to explore the universe with unprecedented precision and detail. One of the most significant breakthroughs in infrared astronomy is the development of adaptive optics and advanced sensors. Adaptive optic systems correct for distortions caused by the Earth's atmosphere, providing clearer and more detailed images of celestial objects. This technology is vital for isolating faint infrared signals from background noise. In addition, integrating machine learning algorithms into data analysis has revolutionized our ability to sift through vast amounts of astronomical data. These algorithms can identify subtle patterns and anomalies that may indicate the presence of technosignatures. Among the most revolutionary achievements is the James Webb Space Telescope, which has already managed to change our understanding of the cosmos in more ways than one. With its advanced infrared capabilities, the JWST allows us to look deeper into space and time than ever before. JWST's primary mirror, which is more than 16 times larger than the WISE mirror, combined with susceptible infrared instruments, can detect the faintest thermal signals from distant stars and galaxies. Essential is the telescope's ability to observe in the mid-infrared region of the spectrum. If they exist, Dyson spheres are likely to emit heat in this range, making them visible to JWST. By scanning the sky for these infrared signatures, JWST could provide compelling evidence for the existence of advanced extraterrestrial civilizations. However, its busy schedule, planned months in advance and filled with many other important research projects, limits the time to search for Dyson spheres. Radio astronomy, in addition to infrared observations, plays no small role in the search for technosigns. The Very Large Array in New Mexico is one of the world's premier radio observatories, capable of detecting radio waves across the universe. Radio waves can provide important information about the presence and nature of technosignatures. For example, a Dyson sphere may emit infrared radiation and radio signals as a byproduct of energy harvesting processes. VLA can detect these signals, offering a different but complementary perspective to infrared observations. Developing and implementing advanced technologies will only improve our ability to find technosignatures. However, the results of the team from Uppsala University are not isolated. Another recent study entitled A Data-Driven Search for Mid-Infrared Excesses Among 5 Million Main Sequence FGK Stars by Gabriela Contardo and David W. Hogg found 53 stars with significant infrared excesses. This large-scale search also used Gaia DR3, 2MASS, and WISE data to detect anomalies in the mid-infrared. The technique involved training machine learning models to predict expected infrared magnitudes based on other stellar characteristics. Stars in some bands appeared significantly brighter than predicted and thus were flagged as potential candidates. After applying additional filters to help avoid false positives, the study narrowed the 4.9 million sample down to 53 stars. Analysis of these findings reveals several intriguing candidates. For example, one of the identified stars shows an infrared excess consistent with extreme debris disk characteristics, which could be mistaken for a technosignature. However, its older age calls into question existing models of planet formation, suggesting either an extended disk evolution or alternative processes. The implications of these discoveries are profound. If any of these infrared anomalies are indeed Dyson spheres, it would provide direct evidence of the existence of advanced extraterrestrial civilizations. However, the scientific community remains cautious. Natural phenomena like dust clouds or the extreme debris disk can also produce similar infrared signatures. Therefore, each candidate requires careful follow-up observations to confirm or deny the presence of artificial structures. The controversy surrounding these findings emphasizes the difficulty distinguishing between natural and artificial sources of excess infrared radiation. Indeed, in general, the vast distances between Earth and potential candidates pose a severe problem. Many of the stars under study are thousands of light years away, making detecting and analyzing their infrared signatures extremely difficult. The farther away a star is, the fainter its signals are, and the harder it is to obtain good quality, accurate data. Some scientists argue that our current understanding of stellar and planetary dynamics is incomplete, and these anomalies may reveal new astrophysical phenomena rather than technosignatures. The search for extraterrestrial life has gripped humanity for centuries, evolving from philosophical speculation to a rigorous scientific approach. Today, scientists use various methods to detect signs of life beyond Earth, focusing on technosignatures and biosignatures. While technosignatures are indicators of advanced technological activity, including large-scale structures like Dyson spheres, unusual energy emissions, or artificial signals, biosignatures, on the other hand, are indicators of a biological activity. These can range from detecting specific gases in a planet's atmosphere, such as oxygen and methane, to surface features indicative of life. Current and upcoming missions are crucial in detecting these subtle signs of life. For example, the James Webb Space Telescope can observe in the infrared, detecting the faint heat signatures of distant exoplanets and their atmospheres. This provides valuable data on potential conditions for suitable life. It's confirmed dozens of potentially habitable exoplanets in the last year alone. Another important initiative that goes shoulder to shoulder with JWST is the Transiting Exoplanet Survey Satellite, which aims to detect exoplanets by observing their transits through stars. TESS has already identified thousands of exoplanet candidates, many prime targets for further study with more powerful telescopes such as Webb. Future missions promise to enhance further our ability to detect technosigns and biosigns. The proposed LUVOIR and HABEX missions are designed to directly image exoplanets and analyze their atmospheres. These next-generation telescopes will provide unprecedented clarity and sensitivity, allowing us to detect even the faintest signs of life or advanced technology. In addition to space observatories, ground-based telescopes like the Extremely Large Telescope and the Square Kilometer Array will play a crucial role. ELT, with its massive mirror, will be able to obtain direct images of exoplanets and study their atmospheres in detail. At the same time, SKA will focus on detecting radio signals from space that could indicate technological activity. The search for life is not limited to looking for existing civilizations. Scientists are also exploring the possibility of life in our solar system, focusing on moons such as Europa and Enceladus, which both have subsurface oceans. Missions such as Europaclipper and potential future missions to Enceladus aim to detect signs of microbial life in those hidden waters. As we continually refine our methods and technologies, each discovery, whether it confirms or disproves the existence of life, brings us closer to understanding our place in the universe. The journey is as important as the destination. It pushes the boundaries of science and ignites our collective imagination. And each innovation brings us closer to answering one of humanity's deepest questions. Are we alone in the universe?
Imagine a theory so powerful that it claims to explain everything from the smallest particles that form the fabric of reality to the most massive structures in the universe. A theory that suggests that our familiar three dimensions of space may just be the tip of an invisible iceberg. But what if this theory, despite its mathematical elegance, has never been directly observable? What if the most ambitious idea in physics remains a mystery to this day, even to those who created it? Venturing into the world of string theory, we explore hidden dimensions, unresolved paradoxes, and the ongoing search for the true nature of reality. What secrets does this theory hold? And why, after decades of research, is it still one of the most controversial ideas in science? In the summer of 1968, a quiet revolution began in the hallowed halls of CERN. Gabriele Veneziano, a young theoretical physicist, wrote a paper that, unbeknownst to him, laid the foundations for a theory designed to unravel the very fabric of the universe. Initially, his work was a modest attempt to explain the strong force, the mysterious interaction that holds atomic nuclei together. But soon this work, entitled Construction of a Crossing Symmetric Reg Behavior Amplitude for Linearly Rising Trajectories, will resonate far beyond its original intent. The scientific community quickly realized the potential hidden in Veneziano's equations. Returning from a short vacation, Veneziano was surprised that his work had already generated considerable interest. It turned out that his model simultaneously solved several complex particle physics questions, which immediately made it a sensation. But at the time, neither Veneziano nor his colleagues realized they were on the cusp of something much bigger. A theory that would offer a radically new view of the nature of particles themselves. It took another 5 years before other pioneering theorists such as Leonard Susskind, Yoichiro Nambu, and Holger Nielsen revealed deeper implications of Veneziano's model. They began to piece together the idea that elementary particles might not be point-like objects, but tiny vibrating strings. These strings, they argued, could potentially explain the variety of particles observed in nature as different vibrational modes of the same fundamental entity. However, the first steps were fraught with difficulties. The nascent string theory struggled with several inconsistencies, not the least of which was the prediction of massless states, which contradicted the short-range nature of strong interactions. In addition, the theory required the existence of a universe with a more spatial dimension than the three we observe, a concept that, to put it mildly, troubled many physicists at the time. For most of the 1970s, string theory remained on the margins of theoretical physics. The field was dominated by the rapid development of the Standard Model, which successfully explained many particle interactions without requiring additional measurements or vibrating strings. Many scientists viewed string theory as an elegant but timely irrelevant workaround. But the story was far from over. The beauty of the mathematics underlying string theory, as well as the persistence of a few dedicated researchers, kept the idea alive. And when the success of the Standard Model began to reveal its own limitations, for example, its inability to account for gravity, interest in string theory began to revive. The seed sown in Veneziano's 1968 paper grew by the end of the decade into a field that would capture the imagination of physicists for generations to come. So, string theory starts with a deceptively simple idea. At the most fundamental level, the universe is made up not of point particles, but tiny, vibrating strings. These strings are unimaginably small, much smaller than anything our current technology can detect. By vibrating, twisting, and folding into specific patterns, these strings give rise to the particles and forces we observe in the universe. Within this framework, the characteristics of each particle, its mass, charge, and spin, are determined by the particular mode of string vibrations. One of the key innovations of string theory is its ability to unify two previously incompatible frameworks, quantum mechanics and general relativity. Quantum mechanics describes the behavior of the very small, like atoms and subatomic particles, while general relativity governs the realm of the very large, including stars, galaxies, and the very fabric of space-time itself. However, the two theories don't fit together well. When physicists try to apply quantum mechanics to the gravitational force, the equations often produce ridiculous results, such as infinite values. String theory offers a potential solution by replacing point particles with strings that can move and interact in ways that avoid these problematic infinities. The elegant merger of the two concepts hints at the possibility that string theory could become the elusive theory of everything, a single theory that could explain all the fundamental forces and particles in the universe. However, the beauty of a string theory comes at a price. It requires additional dimensions beyond the usual 3 dimensions of space and 1 of time. According to string theory, the universe consists of 10 dimensions, 6 of which are compactified or curled up, so densely they're undetectable on our current scales. These extra dimensions are crucial because they provide the necessary space for the string oscillations that give rise to the variety of particles and forces we observe. One of the most speculative but fascinating implications of string theory is its prediction of the multiverse, a multitude, perhaps an infinite number, of universes that exist parallel to our own. Each of these universes may have different physical laws depending on how the strings in them vibrate and how extra dimensions are formed. At the heart of string theory is the concept of supersymmetry, a theoretical symmetry that suggests that every known particle has an undiscovered partner or superpartner. These superpartners can help explain why certain forces, such as electromagnetism and weak forces, behave the way they do. Supersymmetry also plays an important role in string theory because it helps stabilize the theory mathematically and allows gravity to be incorporated into the quantum framework. However, despite its promise, supersymmetry has not been observed in experiments such as the Large Hadron Collider. The lack of empirical evidence for both supersymmetry and the extra dimensions predicted by string theory has led some physicists to question whether the theory is a true reflection of reality or just a mathematically elegant construct. The bottom line is this. String theory, with its intricate predictions about vibrating strings and extra dimensions, has encountered a serious obstacle: a lack of empirical evidence. Unlike other theories in physics that have been confirmed by observation and experiments, string theory remains virtually untested, existing more as a mathematically elegant framework than as a proven physical reality. One of the most ambitious attempts to find evidence for string theory comes from experiments conducted at the Large Hadron Collider. The LHC, the world's most powerful particle gas pedal, was created to study the fundamental nature of the universe by colliding protons at unimaginable speed. Among the LHC's many goals is to detect evidence of supersymmetry, a crucial component of string theory that predicts the existence of partner particles for all known particles. These superpartners, if found, would provide strong support for string theory. However, despite years of searching, the superpartners were never discovered. The lack of evidence has led to growing skepticism among physicists. Critics argue that string theory may be more of a mathematical construct than a true description of reality. Its reliance on higher dimensions that are inaccessible to modern experiments makes it difficult, if not impossible, to test directly. This has led some to question whether the theory is at all provable, a key criterion for any scientific theory. Nevertheless, one of the most notable discoveries related to the theory occurred a couple of years ago, thanks to calculations made by physicists Pedro Vieira, Andrea Guerrieri, and Jo Penandonis. Using a method known as the bootstrap approach, they calculated a specific number related to the quantum nature of gravity. Bootstrapping involves gaining new knowledge about the world by determining what's consistent with established facts. It's similar to a scientific way of solving problems using tools and knowledge already available. This number, denoted by the Greek letter alpha, represents the size of the first and largest quantum correction to the equations of Einstein's general theory of relativity.
Remarkably, their calculated value of A in the 10-dimensional supersymmetric universe fully coincided with the predictions of string theory. The coincidence suggests that string theory may indeed reflect some fundamental aspects of quantum gravity. While this result does not confirm that the theory is the definitive version, it strongly suggests that it is still on the right track when it comes to describing the quantum aspects of gravity. In parallel with this experimental work, the development of advanced computational tools has led to significant progress in understanding the potential implications of string theory. Scientists have applied machine learning algorithms to solve the difficult problem of how the extra dimensions of string theory, the Calabi-Yau manifold, translate into the particles and forces we observe. Physicists like Fabian Ruhl and his colleagues used neural networks to approximate the metrics of these manifolds, an important step in determining how they can generate the elementary particles that make up our universe. This approach allowed the researchers to calculate the masses of particles based on the geometric properties of these manifolds, a significant step forward in connecting the abstract mathematics of string theory to the physical world. However, the debate has become increasingly heated over time. Proponents of the theory point to its mathematical neatness and its ability to provide a potential unification of all forces in nature that no other theories manage to do. They argue that the lack of experimental evidence is not a fatal flaw, but rather a reflection of the enormous challenges involved in exploring such fundamental aspects of the universe. Some even suggest that new experimental methods or future advances in technology may eventually uncover the hidden dimensions or particles that string theory predicts. However, this focus on mathematical elegance has its detractors. Critics argue that string theory's reliance on complex and unprovable mathematics pushes it into the realm of speculation rather than empirical science. They warn that the pursuit of this philosophy may divert resources and attention away from other promising areas of research that rely more on observable phenomena. This contradiction between mathematical beauty and empirical evidence led to a broader philosophical question. Is string theory a true physical description of the universe, or is it just a complex mathematical hypothesis? The lack of direct evidence and the difficulty of making testable predictions led to fears that the theory would never become anything more than an abstract intellectual exercise. While the search for evidence continues, the scientific community remains divided. The promise of string theory as a theory of everything hangs in the balance, and its fate depends on the future of experimental physics and the continued pursuit of a deeper understanding of the cosmos. Black holes, some of the most mysterious objects in the universe, represent a boundary where the laws of physics as we know them break down. At their core is a paradox that's puzzled scientists for decades, the information paradox. According to classical physics, when matter falls into a black hole, information about that matter is lost forever, seemingly violating the fundamental laws of quantum mechanics, according to which information must be preserved. String theory offers a compelling scheme that can resolve that paradox. Strings can encode information in a much more complex and subtle way than classical particles. Applied to black holes, the theory suggests that information that enters a black hole is not lost, but is stored in the strings that make up the black hole itself. This intriguing discovery is directly related to Hawking radiation, a theoretical prediction made by Stephen Hawking in 1974. He suggested that black holes are not completely black, but emit radiation due to quantum effects near the event horizon. This radiation, known as Hawking radiation, gradually causes the black hole to lose mass and eventually evaporate completely. However, Hawking's initial calculations showed this radiation was purely thermal. That is, it did not carry any information about the matter trapped in the black hole. This This led to the alarming conclusion that after the black hole evaporates, all information about the objects trapped in it are lost forever. A direct contradiction to the principles of quantum mechanics. String theory offers a possible solution to this problem by suggesting that the radiation emitted by black holes may indeed carry information, albeit in a highly encrypted form. The idea is that the microscopic strings that make up a black hole can encode information about everything that enters it. As the black hole radiates and evaporates, this information slowly returns to the universe through Hawking radiation, preserving the principles of quantum mechanics. In addition, string theory suggests that black holes are not just astronomical objects, but also the key to understanding the fundamental nature of the universe. The study of black holes in the context of the theory bridges the gap between the microscopic world of quantum mechanics and the macroscopic world of general relativity. In this sense, black holes serve as laboratories for testing the ideas of string theory and exploring the connections between the micro and macrocosm. The insights gained from studying black holes in the context of string theory may eventually lead to a deeper understanding of the universe's greatest mysteries, bringing us closer to a unified theory of all things. As we move into the future, string theory faces both enormous challenges and unprecedented opportunities. Nevertheless, it's not without its competitors. Competing theories like the loop quantum gravity offer alternative explanations for the fundamental nature of the universe. Unlike string theory, which relies on these tiny vibrating strings and extra dimensions, loop quantum gravity attempts to quantize space and time itself, proposing that space-time consists of discrete loops rather than a smooth continuum. These competing concepts are pushing the scientific community to consider a wider range of possibilities in the search for a unified theory. This inevitably raises questions about the very nature of knowledge, the limitations of science, and the boundaries between what's considered empirical science and what can be considered mere mathematical abstraction. Kurt Gödel's incompleteness theorems serve as a profound reminder of the limitations inherent in any formal system of knowledge. Gödel showed that in any sufficiently complex system there's truths that cannot be proved within the system itself. This idea has philosophical implications for string theory. If the research for a complete and self-consistent theory of the universe is subject to the limitations described by Gödel, the question arises: can string theory ever truly realize its ambitious goals? The metaphor of the island of knowledge further emphasizes the limitations of what we can know. As our scientific knowledge expands, so does our awareness of the vast, uncharted territories that lie beyond it. String theory, with its reliance on abstract mathematics and higher dimensions, pushes the boundaries of this island, but also emphasizes how much remains beyond our grasp. The more we learn, the more we realize how little we really understand about the universe. This brings us to a key conflict within the scientific community: the tension between empirical science and mathematical theory. String theory, with its complex mathematical structure, has been criticized for its lack of direct empirical evidence. Critics argue that without experimental confirmation, string theory risks becoming a form of metaphysics, disconnected from the physical reality it tries to describe. Defenders of string theory, however, argue that the mathematical beauty and internal consistency of the theory justify its application, even in the absence of direct evidence. The controversy surrounding string theory echoes a broader historical pattern in science, where mathematical theories often precede empirical confirmation. For example, Einstein's general theory of relativity was initially accepted on the basis of its mathematical elegance, and then confirmed by observations. String theorists claim that their work is in a similar position, awaiting experimental tools capable of testing their predictions. And in fact, this is true. The future of string theory can only be determined by the availability of new experimental techniques. One such possibility is the development of more powerful particle gas pedals or gravitational wave detectors that could provide greater sensitivity. Moreover, ongoing research on black holes and their connections to quantum mechanics and string theory may yield crucial discoveries. As discussed earlier, the study of Hawking radiation, information paradoxes, and the role of strings describing the interior of a black hole is likely to remain fertile ground for research that could unlock some of the deepest mysteries of the universe. Looking to the future, we see that the scientific community remains divided as to whether string theory will ultimately prove to be the correct description of reality. What is certain, however, is that the path to a theory of all things will continue to drive innovation, inspire debate, and expand our understanding of the universe. Whether it's string theory or another system, the search process itself is what drives science forward, and the next few decades promise to be a watershed period in the history of physics that will finally bring us closer to answering the deepest questions about the nature of existence. Until then, stay tuned for those discoveries and breakthroughs that will shape the future of our understanding of the cosmos.